Good day, my name is Timothy Wadikule. I'm here to discuss proving of gamma distribution using moment generating function method. The probability density function of gamma distribution is f of s equal to lambda into bracket lambda x everything raised to power n minus 1 exponential raised to power negative lambda x divided by gamma subscript n, where s greater than or equal to 0 otherwise. Moment equal to integral 0 to infinity exponential raised to power theta x times probability density function of gamma distribution. In equation 2, we use n minus 1 to open the bracket and we have exponential raised to power theta x multiplied by lambda times lambda raised to power n minus 1 times s raised to power n minus 1 times exponential raised to power negative lambda s divided by gamma subscript n. In the third equation, we collect the light times. In the fifth equation, we say let u equal to into the bracket lambda minus theta close the bracket x. When we differentiate u, we have this one. I'll make the x the subject of the formula, which gives us du divided by lambda minus theta. So any place we see into the bracket lambda minus theta close bracket x, we are representing it with u. While any place we see dx, we are representing with du divided by lambda minus theta. So we have this equation. We factorize lambda raised to power n divided by lambda minus theta all raised to power n out of the equation. In equation 3, we take gamma out of the integral and we have this one. According to the rule of gamma distribution, all the things here give us gamma subscript n. So therefore, gamma subscript n cancel gamma subscript n in equation 4, and we have lambda raised to power n divided by lambda minus theta all raised to power n. N common to both numerator and denominator, so we take it out and we have into bracket all raised to power n. We divide all the equation 6 by lambda and we have the moment generation function of gamma distribution to be into the bracket 1 minus theta divided by lambda raised to power minus n. To obtain the expected value of gamma distribution using moment generation function, we need to differentiate the moment generation function we obtain. When we differentiate it, we have negative n into the bracket negative 1 over lambda close the bracket and open another bracket 1 minus theta divided by lambda all raised by minus n minus 1. Here we multiply negative n by negative 1 divided by lambda and we have n divided by lambda. So when theta equal to 0, we have the derivative of moment into the bracket 0 minus n divided by lambda. So therefore, the expected value of gamma distribution using moment generation function is n divided by lambda. Here from the above, we differentiate the above equation and we have this one. And when we have this now, by multiplying into the bracket negative n divided by lambda into bracket n plus 1, close the bracket, open another bracket, negative 1 divided by lambda. When we multiply everything together, we have n into bracket n plus 1 divided by lambda square. And this one also. So when we say theta equal to 0, the second derivative of moment generation function into bracket 0 give us n to bracket n plus 1 divided by lambda square 1 raised to power negative into bracket n plus 2. And the second derivative of moment generation function with gamma distribution equal to n to bracket n plus 1 divided by lambda square. So variance of gamma distribution using moment generation function now equal to n into bracket n plus 1 close the bracket divided by lambda square minus n divided by n all square. Now open this bracket, we have n square plus n divided by lambda square minus n square divided by lambda square. When we take the LCM of both equations, we have lambda square. We have n square plus n minus n square. So therefore, n square cancel minus n square. We have n divided by lambda square. So therefore, the variance of gamma distribution using moment generation function equal to n divided by lambda square. Thank you. Please do well to subscribe to my channel. See you next time.